All right, so we're recording now, and today basically I'm kind of combining two lectures, and that's okay. And so we're going to spend a little less time on the first part, which is the Python part. I had you do an exercise last week, and as part of the lab last week. Um, and we do offer a whole course in scripting, so you could take that. It's actually offered next semester if you're interested in it further. Now I was going to start by opening that project, and basically the project that we did last year, temporal modeling, and implement the loop part as a script. The class gets way into Python and different data types and variables. But today we're going to talk about it mostly just as a way to execute raster functions a little bit more quickly, or I guess with a little bit more automation available. So I need to open the project from last week, but Kevin came and he logged me in as like an administrator on this computer. I just remembered that. So where did I put? Is that where I put it?
Well, it'll be under your user.
Oh, there's this GeoAdmin.
Go to your numbers.
Well, I wasn't logged in as me last week.
You were logged in as an admin last week?
Yes, because Kevin came and I needed to install something, and so he logged me in. So my oh, but you know what? Let's see. Okay. Yeah, you're right. It might not let me access those. Well, what we'll do maybe is actually start off with the first part of the lecture, and then after the break we'll do the Python part, because they don't really have a whole lot to do with each other. We could implement one using the other, and then I'll send an email here on my thing and see if I can get Kevin to send me the username and password, and so we'll do the Python part after the break. Hold on a second. Okay. All right. So I was going to post the toolbox that I started as well. So I do need to get that. Oh, I did? Well, if I posted the toolbox, then I'm pretty sure. So that would be in here. I'm pretty sure we could just based off of that. If I can't get in with later, then I'll just do that. I might have to repair a few of the links, but we can do that. I can do that during the break. All right. So I'm going to go to today's topic. Now, today's topic overlaps a little bit with our courses in remote sensing. So I can't see your hands, but if who's taking a remote sensing course? Got one up here. We've got Heather down there. Anybody else down there? Okay, so we've got a few people that have taken a remote sensing course, and it's been a little while. I used to teach those courses. It's been a little while since I have, and so I don't remember, or I don't know exactly where this topic gets placed in the two courses that we've taken that we talk about, and so there may be some overlap here, but we're going to talk about how these are implemented in GIS software. Some people aren't even aware that this task that does seem a little bit more like a remote sensing task is available for use inside of a GIS system. But strictly speaking, I wouldn't really even say that it is a remote sensing task. Yeah. Yes, I am recording. Thanks. Just verify that. Yep, been recording for about 13 minutes now. So, is a remote sensing task. It is fundamentally a raster GIS operation. And so we're going to talk about that today. And I know that it will probably be covered in greater detail. This is probably 2 or 3 lectures in a remote sensing course where you're doing that. But technically, classification isn't raster classification isn't even something that you have to do with images. You could do this with other multidimensional data. So if you had, let's say, a multidimensional data set that represented some other quantity that had been derived from interpolation. We talked about interpolation earlier this semester. Data in the field, like I don't know if I've showed this example before, but you get like currents in the ocean that are derived from floats that are out in the ocean. Yeah, it looks like I'm going to be able to get that. So let me just turn this down. You could do this with any data set. Typically, classification is done with a multidimensional data set. In other words, in raster context, we usually mean a multi-band raster. So it has multiple data sets. Although you could do it on one data set, at that point, it's kind of like a what we would usually refer to as a hand classification or a density slice operation in remote sensing literature. Before I get too far on this, I'm going to download the, that's open. I'm going to download the example so I can work through it, and I'll kind of show you what I mean. So modules. So I have this data that I'm going to use for today's lecture, and you're going to use it in the lab. This data is hot off the press. It was just collected April 1st. Anybody know about Planet, the company Planet?
Yes. They have a bunch of satellites.
They have a bunch of satellites, and how big are they?
Tiny.
They are tiny.
250 maybe.
Oh yeah, there's the guys.
They're actually like a little bit bigger than a shoebox. So they're really small data sets. And so I'm going to go ahead and add that. I'm already have this open, so you can.
3 meter resolution.
It is. It's 3 meter resolution. Good job. And there's dozens. I forgot exactly how many there are up there, and they're probably adding more all the time. And with an EDU email, you can sign up to actually download. I think it's 100 square kilometers a month for Planet data. Yeah. So I can send you the link to do that. I should have just put it up there, but I have a EDU email address, and so I downloaded it. Now, okay, so I put it. I don't even know where I put it. Oh, but probably put it in downloads. Okay, so here's the Planet data that I'm talking about. Should have put a picture up of the satellite, but you could just Google Dove satellites. I mean, really, it's just like it's basically a digital camera, like a DLSR that's up in space, that's up in orbit, because it's about this big, and then it's got two solar things that allow it to get solar energy, and that's it. And beam the information back down to Earth. It's a great idea. Some of the old sensors like Landsat that have been around for a long time are as big as Volkswagen. Okay, so this is the data set. Where is this, by the way?
That's here.
Yep, that's here. That's Hattiesburg. So this is like Serene out here, yep. Canebrake, the sewer ponds, exactly. And then this is downtown Hattiesburg, and we're somewhere over here. well, us four. I realize y'all are down there, but we're in this building right here. So you can see that the spatial resolution, it's not like a drone or anything. Okay, so what I was referring to earlier, I remember back when we did this, you can go in here and add just a single band of data, right? So I could add just band 4. So let's say I was not using a multi-band data set. And let's say I just want to separate water from land, right? I don't need a fancy classification algorithm to do that. I just need to decide, what is the cutoff? Because water is darker than land. So what's the classification to cut water off from land? So I could just go into classify and change the number of classes to 2, and then just fiddle with it for a little while. There used to be a way to I guess I just have to go in here. Anyway, I just fiddle with the symbology, manual interval. I'll get back to there we go. I want to not show the statistics anymore. I'll get rid of those. Anyway. Guess I'm stuck with the statistics. Oh, hide statistics. Oh, show statistics. There we go. Okay. So obviously what I'm showing right now is it's not water and land. But if I went in here and played around with this value, I could find something closer to what the water was. So it looks like that's the yellow already includes water, but it includes things that aren't water. And so I probably need to change the upper value here so that I encompass more. So I could just throw in, 12,000. Still that's too much. Let's go all the way up to 20,000. Well, that's already more than that other one. Oh no, sorry, I'm going the wrong way. This one needs to be lowered because the pixels are darker. So let's go down to 15,000. I guess. Yeah. Good. So 1,500 is about right. Sorry, 1,500, not 15,000. Thanks, Forrest. So now you can see that most of the water shows up as one color and the land shows up as another. There's really nothing else that we could do. There's nothing else that would improve the algorithm for figuring out what was water and what was land that only considers pixels. And there are other ways to do it. We'll talk about that later today, but we could start to look at the shape of things, and if the shape of things help us to determine whether something was really water or not, then we could use that as a different variable. Okay. But water exists in all different shapes. I mean, these aren't water. Obviously, this is probably, it's probably, that's a shadow. See how these lines here are the shadows of these trees that are cast onto, what is that, 40th? Yep. I don't know if we could improve this any further without. So that's one of the things about classification is you're going to get errors. Right. All right. So usually it's a multi-band raster. Yeah, you can continue to go into it rather than adding it. And you can add one of the bands. I had just added band 4. All right, so fundamentally, classification is assigning pixels to classes or categories. We've already covered that. I'm going to make this presentation now. So what we're doing is we're arriving at classes, and in theory, these are homogeneous classes. Okay, so here it is, kind of digitally. So our image data set is just like this hypothetical image data set that has 4 channels per pixel. In other words, 4 bands. Sometimes they get referred to as channels, sometimes bands. I like bands a little bit more. It's more general, but I copied this from a textbook. Okay, so if you can imagine the values in each of these 4 bands for the same location, okay, those form what we refer to as a signature. In other words, there's 4 different values at that location. One for, let's say, red, green, and blue, and near infrared. However, they don't have to be image values. One could be red, green, and blue, and the other one could be population, if it was known or derived, or the other one could be precipitation, if that was derived, and we had a raster data set representing that. That's the point I was trying to make earlier, is that they don't have to be image data. So then, once we have those 4 values, we compare them to the ideal measurement of that particular object. So we know that on average, urban pixels tend to look like they have a value of 110 for band 1, 99 for band 2, 78 for band 3, and 9 for band 4. Whereas water pixels have a different set of values. Okay. These values are derived through observation. So we basically say, this is water, this is urban. We know those values. And so we're comparing these values, and then for every pixel, we do a comparison. So it's doing it, it's basically a local operation. It's for every pixel, it's comparing these 4 values and finding out which one is the closest. Okay? So the definition of which one it's closest to is the basis for different classification algorithms. Is it closest to urban? Is it closest to river? Is it closest to forest? Or so on. However many classes we have. So when I say based on training areas, a training area means a observation. So it's the task of extracting thematic classes from a raster image. So we're turning, usually, almost always, continuous data, whether or not it's collected from a remote sensing source, into categorical data, into a thematic class. So yeah, so basically we have a lot more spatial data to work with now. You know, we've got satellites, which is what this is an example of. We've got airborne sensors, and we've even got drone sensors now that collect data. And obviously, this is showing the exact same area mapped, but in reality, typically we measure relatively small areas with a drone, large areas with an airplane, and very large areas with a satellite. So, yeah. So what can we use this for? Well, the primary use is to create a map of land use, land cover. Lots of different GIS applications for maps of categorical maps. So we're basically turning data into information, this process of converting converting raw data into information, which is a lot of what we've done for other parts of this course. But here's a few applications, a few different groups that would use them. Maybe that should be indented a little bit. And then it also can be used as an intermediate step in order to derive other information in a GIS database. All right. So we refer to a classifier as a an algorithm that's implemented as a computer program that does some sort of image classification. There are many different types available, and there's no one method that's best, although I will talk about one that's often set up as the standard later today. So under geoprocessing, these are implemented in the let me just find there we go. Where is it implemented? I forgot what toolbox it's in. I always just search, but I want to tell you guys where it is. So it's in Spatial Analyst tools, but where? Let me see if I can find it again.
Segmentation and classification.
That would make sense. All right, so under Spatial Analyst tools, we're talking about Spatial Analyst. I should have just looked. I would have figured that out. Okay, spatial segmentation and classification. So there are a number of different classification algorithms that are even implemented in ArcGIS. And if you've taken a remote sensing course, you might recognize some of these. So we've got classify raster, which will you classify based on a process. We've also got some other things. We're going to talk about these as we go through the course. So there's the maximum likelihood calculator or classifier. There's a random trees classifier, and then there's some other ones that have been added even since I taught this last time. Now they're starting to implement these tools for deep learning. However, and I did put that on the syllabus as one of the things that we would talk about, but they're still not coupled very well. So although you can export training data for deep learning, implementing the deep learning is kind of beyond this course. But maybe I'll be able to show that later. Eventually, I think that they'll have that tied right into ArcGIS. Okay, but for now, we're going to focus on these other more traditional ones, and you're welcome to explore that because the workflow is very, very similar, but the classification is done outside of ArcGIS. So the simplest type of classifier is a spectral classifier that we already talked about before. It's basically a local operation. It considers each pixel individually. It can work fairly quickly. It's computationally efficient to just go through pixel by pixel and then decide which class it's closest to. Okay. One of the weaknesses is that it doesn't consider context, which is one of the powerful aspects of geography is its situation. So it's very good for kind of basic classifications. If I want to decide, is this a tree? Well, not is this a tree. That's a bad example. Is this a forest? Or do I want to know if it's an urban area? That's pretty good for a pixel-based classifier. However, if I want to figure out if something is a shopping mall or a megachurch, then I might need some contextual information in order to find that out. And one of these other classifiers would be better. So there's spatial neighborhood classifiers, which basically utilize neighborhood operations to examine the neighboring pixels. It's a little bit more difficult to implement. Can be more expensive computationally, and even dollar-wise. And then the most advanced one is an object-based classifier, where the first thing that it does is segment the image into similar spectral regions. You think of them like, it calls them segments. Think of them kind of like polygons, and then classifies the polygons based on their properties and also the proximity to other polygons. Okay, this was really helpful. This type of operation is probably pretty helpful for that deep learning type of an operation. So some things that I've seen implemented in ArcGIS, I just went to that conference a couple weeks back. ESRI had a demo on using object-based classifiers to define swimming pools. And then it took it even further, and they were finding swimming pools that were like off, like people were not maintaining them. In their headquarters in Redlands, so the example was implemented in Redlands. All right, so another way to classify classifiers is whether or not they're what we call supervised classification or unsupervised classification. So supervised classification is what you would normally think of, where you come up with the classes, you say, I want to find all the forests, or I want to find all the swimming pools. Here's some examples of swimming pools, or here's some examples of forests. Find the rest of them. That's supervised. Unsupervised says, hey, there's patterns in my data. You find them and tell me about things that look similar. And then I'll assign a label to the different classes that you find. Okay. Sometimes the process is actually implemented as a mix of the two. In other words, I might do an unsupervised classification first, identify a few classes, and then if there were still other classes to find that weren't, I might mask out those regions that were already classified and reclassify the rest using a supervised technique. Or I could do an unsupervised classification and then use those as clusters to implement an object-based approach. All right. So the way that this is normally implemented is through a two-step process. The first step is to train or to point out to the computer where there are different classes. So here I'm saying, okay, A is water, B is agriculture, C is rock. I'm pointing out where those classes exist. And then the second process is to use the information about those areas and the different bands in the raster data set to arrive at a classification output. So that's what you're gonna implement today. Well, when you get around to it. So in ArcGIS, the way that this is usually done is that you come up with you draw polygons that represent different classes, and then you'll train your maximum likelihood classifier. All right. So we're going to talk about unsupervised classification. So unsupervised classification is nice because you don't need to know anything about your data. You just say, hey, group everything into similar things. So you don't have to specify what the information classes are. It just shows you the groups that already exist in your data. It tries to spectrally separate the pixels. So the things that you have control over in an unsupervised classification, this is one of them, ISO cluster, is that you have control over the number of classes. So here's where you specify the number of classes, or the maximum number of classes in this case. Okay. You also it's gonna weed through your data multiple times. That'll make more sense when we talk about how it actually works here in a second. And so you'll get to be able to control how precise it gets and things like that. So there's two main algorithms. ISO data is really kind of k-means extended. So I guess you shouldn't say two main algorithms, but there's ISO data and k-means. So we'll talk about how those are implemented here. This is really the same as this. All right. Most of these slides are taken from a book called Digital Image Processing by John Jensen. It's the book that I used in the remote sensing course. I don't think Dr. Carter currently uses the same book. Not the slides, the pictures. All right. The result of a classification is that you're going to have informational classes. Now, your pixels aren't informational classes. So whether you do an unsupervised classification and you get a result that is a bunch of clusters, or you specify the clusters, you're going to end up getting informational classes. A spectral class is what an unsupervised algorithm finds. It's things that look similar spectrally. Okay. So you need to think about the difference between these two, because sometimes if you're trying to find forests can actually look pretty different spectrally, right? Some forests look a lot different than other forests. And in order for your algorithm to work right, you need to have relatively homogeneous areas. And so if you have forests that look significantly different in the data, in other words, their digital numbers are significantly different in the data, then it may help your classification algorithm to divide those up. So you can have old forests and young forests, or wetland forests versus upland forests. Make those two different classes, and that can improve the classification process no matter what algorithm you choose. Okay. All right, and we'll talk about why that is here in a second. So informational classes are usually composed of numerous spectral classes, but you're going to want to train your algorithm using spectral classes and then combine those up to informational classes. Okay. All right, so we're gonna want to examine how pixels within a class. Basically, the way that it assigns or defines which class a particular pixel is in is the standard deviation or the variance and the mean of every class. That's how it works. So just as a review here, this is a normal distribution. So let's just say we circled a big area that represented forest on our map. So go back to this guy. We circled an area right here that represented a forest, or this area right here, right? Is there variability? Are all those pixels the same? Are they similar? They are similar. So if I circled this area right here and said, okay, all the pixels in that image, if we graphed their value, let's say in the near infrared band, we might get a bunch of them here in the center, but we'd have some brighter ones and some darker ones, right? So the distribution of the training data that we circled might look like this, where there was a mean, and then there was a particular standard deviation or range associated with those. Okay, so here's training data for like 4 different classes. We can already see there might be a problem here because 3 of these have almost the same mean, but with different standard deviations associated with them. Okay, so you're going to have trouble distinguishing between these classes. Now this is only for one band though. Okay, in real life, every single training data set has n number of means and n number of standard deviations, where n represents the number of bands. Okay. All right, so we can try to separate it just based on the mean data, but that doesn't really always work, even if we normalize that by the standard deviation. I'm gonna second. I don't know if I taught that as well as maybe I should, but I have a few more slides in here that kind of talk about it a little bit more. Okay, so I'm going to skip down here and then I'll come back. Okay, so what I was getting at before is that there are, and this is directly copied from the digital image processing book. But let's say here's band 4 and band 5. We don't have five bands in our data set. So think of this as band 4 and band 3, let's say. So these are all the pixels in the image. So pixels that are bright in both band 5 or band 3, whatever we want to say it, in one band, and they're bright in band 4 are way up here. Okay? And pixels that are dark in both are down in this corner. And so the center of these dots, the circle, represents the mean for band 5 and the mean for band 4. So the mean for band 4 is right here, and the mean for band 3 is right here. And so these are kind of like, this is one standard deviation out. So these boxes are one standard deviation in each direction. And so anything in this box, we could say, well, that's definitely in this class, commercial. The problem is, what about these things? What about these other pixels? Which class are they in, right? And so that is the kind of crux of different classification techniques or spectral classification techniques. Okay. So that's what we're talking about here. So this is just one-dimensional. That other one was a two-dimensional representation. There's a few other slides here that kind of show it in maybe 3 dimensions here. Here's another one that just shows it in 1 dimension. Okay. All right. Let's see, where was I? So now we're going to talk about unsupervised classification. Okay. So images are usually composed of several relatively uniform spectral classes. Unsupervised classification is the identification and then labeling and then mapping of those classes. Okay. We already kind of talked about that. Doesn't require a lot of human interaction, any knowledge. You don't have to identify areas, so you skip a whole step in this process. It's a lot faster on the front end, but then you have to go through the effort of examining the different classes on the back end. Okay. So the simplest way to do unsupervised classification is to identify a few means in your data and then finding the distance to the center of those clusters. So let's talk about finding distance real quick. Okay. This is the Pythagorean theorem: a squared plus b squared equals c squared. So if we only had one band that we were considering, the distance, two bands that we were considering, like this, back down here. If we had 2 bands that we were considering, the distance from this pixel to that pixel is, we can just use the Pythagorean theorem to find it. Okay. That's what this is referring to. Okay. Now, what happens if we have 5 bands or 10 bands or 20 bands? Well, the software can still find the Euclidean distance. It involves a lot more math, but it's still just the Pythagorean theorem in theory. It's the minimum distance in n-dimensional space. So there's more space associated with it. Okay. So it could be extended to multiple bands. So you could think about every single pixel having a distance to a cluster center, and that will help us to determine which class it's in. Right. So here's 2 different bands from Landsat. Landsat's an older satellite. Like I said, it's like the size of a Volkswagen, and it's been collecting data. There's been numerous versions of the Landsat satellite, but since the 70s. Okay. So this might be this is what we refer to as a spectral plot, if these really are spectra. I mean, who's to say band 1 is necessarily spectrum, but it could represent elevation, and this could represent red reflectance. Okay. But you could see in this data that there are some obvious classes, right? So here, these classes are grouped. What k-means does, since it's unsupervised, is it places a user-specified number of clusters randomly throughout the spectral space. So in other words, it would start with these are random clusters right here, right? Okay, and then it iterates through and finds out what the true center of that cluster is. So for all, if this starts out as the center, it finds the center of all of these values, okay? And that center is going to move down toward these values because there's more down here. Okay. And then it finds the standard deviation, and basically that has the effect of cutting things off outside of the standard deviation. So the new cluster is smaller and it's more focused in this direction, whereas this cluster has moved over and encompassed some of those other values. Okay. So this has an effect of moving the values closer and closer to the center of various clusters. So it's going to iterate through it, and as the user, you specify the number of iterations. So the mean location is reclassified at each time. Now at the end, let's say this represents a point where it's stabilized. In other words, the clusters aren't moving. The cluster centers aren't moving very much anymore. At that point, all the pixels are classified into the closest cluster. So even though this one right here isn't inside this standard deviation ellipse, it would be classified into that cluster, and then it produces a map. So that's the way k-means works. Okay. So it is dependent a little bit on the class centroids that it comes up with at the beginning. So if you run it again, it may have a different answer. And how it measures distance, usually we use a Euclidean distance, but there are some algorithms that use different methods for measuring distance. And then how it decides what the classes are at the end, it's going to usually, it will report how distinct a certain class is. In other words, this is idealized. See how all these circles, there's no overlap? But in reality, there might be an overlap between two different clusters. And in that case, it will have to report the distinctness of those particular classes. Okay. All classification programs try to determine classes based on decision boundaries. So at the end, there'll be a boundary associated with each of these, not just ellipses. Every single pixel will fall into one of the classes. Okay. So the way that that's done is one way is to find the minimum distance to the means, determines the point's equidistance from a class mean. The second one is the nearest neighbor, determines the point's equidistance from the nearest member of two classes. So here's some examples of that. Okay. So here's the decision boundary based on minimum distance to means. Here's a decision boundary based on nearest neighbor classification. They're not really all that different, especially in these two cases. There are different ways that you can implement different discriminant functions. Typically, you have at least, I said before, you don't do this on single band data. Typically, you don't even do it on two band data, but you can. Typically, you need to have at least 3 features or dimensions. In other words, 3 raster bands to really get some separation in your classes. Okay. I think I organized ISO data down to the bottom here, or maybe I didn't even include it. Yeah, here we go. I shouldn't have done that, but ISO data is another algorithm that extends k-means. So this is slide 58, by the way. It also calculates the standard deviation for the clusters, and what it does is it evenly distributes the initial clusters throughout feature space. That's how it starts off. Okay. And then it works very similar to k-means, where the clusters move through feature space based on the average of the values that are considered part of its cluster. And so it'll go through each of its iterations and produce a result like that. All right, so I should have organized that back up with because that's another unsupervised algorithm. Okay, let's go. Let's talk about supervised classification. This is what we'll be implementing today. Well, actually, you're gonna do an exercise of all three, but I'm specifically asking you in the lab to do a supervised classification technique. So you'll need to know that you start with the different classes. You decide what the classes are. Okay, you choose them. The operator chooses them. Then you have to create training samples for each class. In other words, you have to define polygons that represent water, that represent forest, and so on. There are quite a few algorithms. Parallelepiped is one that's kind of like minimum distance to means, but it's in 3-dimensional or 4-dimensional, 5 n-dimensional space. So we're going to talk about that a little bit. Maximum likelihood is another one that is used a lot. Okay, so here are some of the advantages. All right, disadvantages. So one of the main disadvantages here is that that you have to specify the classes, and as such, you're introducing some bias into the process. Okay. I put a lot of information that's repeated on this slide, sorry. There we go. So, yeah. So basically, remember when you're coming up with these these classes, that they should be spectral classes. Even though your end goal is often informational classes, they should be uniform in their spectral properties. And you're not going to get good results if your spectral classes are significantly different, especially if they kind of like span two totally different things, and there's another class that looks kind of like the average of the two. You're going to get really bad results if you do that. Okay, so all right. Okay, so there are a few different ways to specify your training data. You can actually, in ArcGIS, you actually draw them as polygons. So sometimes you can recognize the classes right in the imagery you're trying to use. However, sometimes it's a little hard. You're going to have to use ancillary data. You might have some higher resolution data. You might have to go out into the field, drive around, and look and see what things are. So we did this a lot. We were trying to create some benthic habitat maps down in the Caribbean. So in other words, we're trying to come up with classes of things that are underwater based on just the spectral properties that we can observe from satellite. And so we can say, oh, that's a light area, that's probably sand. But do we really know it's sand? So we went out on a boat and dropped a camera off and looked underneath and found out, yep, it's sand. Or, no, that was some other light object that's underwater. And so sometimes you have to go out and find those areas, okay? And then you can use those points as training data. You say, yep, that was sand. That would be considered ancillary data. Field work is often necessary to verify. Okay? We're not going to do any field work in this class. So, all right. So, what else does your training data have to look like? Well, for one, you have to have a certain number of pixels. Okay, because we're dealing with statistics. Okay, what is statistics? Well, statistics is inferring other measurements based on. Basically, we're inferring these classes based on calculating the means and the standard deviations of those classes. And so we need to get a significant number of observations in order to make that inference. Lots of times statisticians will talk about having adequate sample size. So that's really all we're talking about here, is having an adequate sample size. And there are lots of different rules of thumb, and there are actually calculations that go into these. But for this class, we're going to say you definitely want to spread around your training areas. So if you draw a box here in this forest, even if it has 100 pixels, I wouldn't call that good. I would find several other examples of forests throughout the image. Okay? So your training data should be as extensive as the observations of that particular class. So if they only exist in part of the image, then you can find some examples that exist only in part of the image. But if forest is pervasive throughout the entire scene, you should have examples of forest from the entire scene. Okay. Right? You can already, like I already gave an example here. See how these forested wetlands down here, they do look different than let's say this upland forest over here. Okay. Actually, that's kind of a mix because there is some bottom. You can basically see these brighter pixels because there's a little stream channel coming up here, a little stream channel coming down there. That's it's causing those brighter pixels. But yeah, there's some just pine areas right here and some mixed areas down there. But you can see these are definitely deciduous bottomland forests down there. Anyway, kind of got off track there. All right, so you want to have them spread out throughout the entire range that particular class exists, and you want to have a total of at least 100 pixels per class category. Okay. So the number depends on the number of categories, their diversity, and the resources available. Okay. So yeah, you can examine the means and the standard deviation for each of those classes and see if there's a lot of overlap. Okay, there are tools for doing that. Well, there are reports when it actually goes to run. That's accuracy assessment. We're not going to talk about accuracy assessment today. Well, we'll talk a little bit about it, but we're actually going to implement it in a later class. Okay. So the shape is usually not important for spectral classification. Okay. So lots of times I just draw rectangular things, or if I can draw it quickly, it can be a little bit irregular. Okay. So it's not really that important. So like I said, these are kind of repeats spread throughout the image, large enough to get the spectral characteristics and the variations. Right? But this is key right here. Each training set should be as homogeneous as possible. Yeah. Now there is some legitimate variability in a particular class. You want to capture that. But if a class has too much variability, you ask yourself, is there really more than one spectral class here? And if there is, divide it in two. Even if you only care about forests, you should divide it in two and then find one type A forest and type B forest. Or with water, type A water and type B water, and then group them at the end. All right, so this is the sequence. This picture is from an ESRI literature. So this is kind of like the process that's involved here. This is from a textbook, right? So you assemble information, conduct field studies. If it's possible, go out, find some different areas, and then look at your image quality, find available imagery. Okay. Then we start right here. We identify our training areas. That's what we're going to do today. We're going to evaluate the training data and edit the training data if necessary. And then we do this part. We prepare the raster, choose the classification schema, train the classifier, and then classify the raster. And then finally, like I said, we're not going to talk about this. We'll talk about it a little bit. We're not going to implement that. Is to evaluate how well we did. Okay, parallelepiped is really similar to just finding the closest, the center, these boxes. These boxes represent one standard deviation out. Either you're in the box or you're the closest you can be to the box. So that's how the parallelepiped algorithm works. It's just an idealized, mostly for teaching purposes, classification algorithm. Okay, so this. Let's see. I don't even know if that's implemented here in ArcGIS, unless it's under here. Let's see what this is. Now this is that's different. Yeah, so yeah, that's not implemented strictly speaking. So we do have the maximum likelihood calculator, which we're going to talk about here in a second. Okay, so here is the example of how the output might look from a parallelepiped example. Okay, so these are all the pixels in feature space or spectral space, not in actual space. And here is the result. It's a mathematically simple algorithm. It's either inside the box or it's closest to the box, the nearest neighbor. Okay. You're going to get some overlap a lot of the time. So this is idealized. This is what often happens. And in which case it would default usually to the minimum distance to the mean. So if this particular value would probably get classified into this class, whereas something that was right there would probably be classified into that class. So typically, what's actually implemented is this thing called the minimum distance classifier. I'm sorry, parallelepiped, it defaults and uses the minimum distance classifier in situations where there's overlap. Okay. All right. Now, yeah, that's what that is. So the pixel is designated to the class with the shortest distance back to the mean. Right. Okay. It's a pretty simple, mathematically simple algorithm. It's just looking at the minimum distance. Okay, so the next algorithm that we're going to talk about, this one's actually implemented in ArcGIS, is called the maximum likelihood, and it's a supervised classification technique. So just like the other ones, the spectral variance and the covariance between each bands are calculated. In other words, it's that, you know, it's this spread in n-dimensional space is calculated. The class can then be statistically modeled with a mean vector. All that means, what's a mean vector? That sounds like some complicated math term, but we have more than one mean. We have the mean for band 1, the mean for band 2, the mean for band 3, the mean for band 4, the mean for band 5, and so on, if we have 5 bands. So the mean vector is the mean for each of the bands. And we need to calculate the mean for each band in order to figure out how far away every pixel is from each band. Okay. So, and then the covariance matrix says, okay, how much is for each training data set, how much overlap is there between the variance in this class versus the variance in this class. One thing that it does is it assumes that the classes are normally distributed. What that implies is that it's even more important that for this algorithm, it's even more important that your spectral classes are homogeneous. In other words, they'll have a specific mean and they'll have some variability about that mean, but they'll have roughly the same amount of decreasing variability in each direction. So they'll look, basically, they're implying that they'll look like this. Okay. All right. So when you make targets in your data set, when you define targets, and we calculate the mean and the variance for each of the classes, what we can do is, because we assume that there's a normal distribution, we can place any particular raster cell in that three-dimensional space and determine the probability that it's in every single class. Rather than determining the distance, we just determine the probability associated with it being in any given class. Okay, so we assign the new pixel to the class with the highest probability. Okay. So one way to think about it, if we only had 2 bands, is that each of these mounds are the probabilities that a pixel is in a particular class. Okay, and so if it's in this mound, it's going to go in that class, and if it's this mound, it's going to go in that class. The kind of marginal cases are the ones that are like out here. Which class is it in? Well, each of these distributions exists in three-dimensional space, so it's just a matter of finding out which mound is causing it to be higher at this location. Is it this mound? Is it that mound? Is it that mound? That's causing it to be higher. And it's hard to see, in this diagram, but mathematically it can be discovered. Okay. You can specify at a certain threshold of probability that you want the classes to specify that there's nothing there, that it's undefined. That's what this means. You can say it's unclassified if all the probabilities remain low. But typically, the idea is to come up with a class that represents every single pixel in an image. Okay. So here is a straight down view, something like this. It's a different data set, but a straight down view of maximum likelihood example. So these are the ISO lines of this three-dimensional surface here. And you can see, well, there's not really any real overlap here, but what if this circle overlapped that circle just a little bit? Well, if this ISO line represented a 10% probability and this ISO line represented a 30% probability, then anything that was in between would go into this class and not this class. Okay. So that's how that works. Right? Now here, this one would remain unclassified because it looks like it's not associated with any of those. Okay. Number 2. All right. So maximum likelihood classifier. Historically, it's produced the most accurate classification results in a general sense. In other words, it's been around a long time. It's tried and true, proven to work. And so oftentimes when people develop new algorithms or new techniques and they publish them in research finding, they'll almost always compare it to a maximum likelihood classification. So that's kind of like the standard. Okay, I developed this new object-based classification scheme, and I'm going to talk all about how it works in my research article, and then I'm going to compare that to just doing a regular spectral maximum likelihood example. Okay. All right. It is a little more mathematically complex, but on today's computers, it runs fairly quickly. You'll be fine operating on this. I think it's a 130 megabyte data set that I downloaded. I downloaded from Planet. Okay, talked about ISO data now. Okay, let's talk a little bit about ground truth. So, ideally, like I said, you go out into the field and find it. This is particularly true if you've never been there, or if it's hard to observe. The classes that you're trying to come up with are hard to observe in the imagery. Okay. All right. Okay. Ancillary data. So what I mean by ancillary data is data that's not imagery data. And one of the things that I think people do a lot is think, well, I can only apply these techniques to imagery, to image data. And that's not really true. Any raster data you can throw in to your process, okay, to your classification process. So you can use other data to assist in your classification. You could also use other data to assist in the analysis itself. Okay, what type of data? Well, if you've got other vector data, other maps, things like that, and then sometimes you can use derivatives of raster data as another band. So you might have red, green, blue, near infrared, and you might throw in NDVI, which we're not going to spend a whole lot of time talking about NDVI, but it's a ratio of the red to the near infrared, and that might produce better results. We could do a simple classification that did water, non-water, and then use that as another data set in another classification process and say, okay, if it's water, I want to classify it different than if it's non-water. Okay. The only requirements for including your other ancillary data is that it has to be raster data. Okay. Obviously, it has to contribute to the overall solution to the problem. I mean, if you don't think it's going to add any value by including a different raster data set, then don't do it unless you're genuinely curious, right? But what does it mean that it's compatible with the raster data? Basically, what that means is that your data has to be in the same scale. It has to have the same resolution. You have to think about the date. If the date matters, like let's say you have a data set that represents imagery, and then you want to throw in another band that might represent precipitation. But if it was collected at a different time, it may not help, or it may not be as good as if it was collected at the same time. Depends on the answer to your question, but you definitely have to think about data. And then accuracy is kind of tied into the scale and resolution, but it may not have the same level of precision or accuracy, and therefore would not really work in your data set. Okay. So I kind of talked about this before, but one thing that you could do is use ancillary data to stratify your data. In other words, you could subsection out different elevation data, because vegetation often changes based on elevation. So you could subset out, you could use an elevation data set to subset out all the really high areas, and then classify those areas using the classification algorithms we talked about today. and then subset out the lower and come up with a different classification algorithm. That way, your spectral classes might be able to be more pure. Okay. And then another way that you could utilize ancillary data is after a classification is done, when you're doing a assessment on how accurate it is. That's what I mean by confusion matrix. Okay, we'll talk about that in the coming weeks. But a confusion matrix could be broken out by a particular data set. So you could say, well, in the lower elevations, I was much more accurate than the higher elevations, or in water, I was more accurate than some other in some other areas. So you can use your ancillary data. That doesn't necessarily have to be part of the classification itself. It can be brought in other portions of the process, in other sections of the process. Okay. All right. Now I'm just going to bring this up real quick, but you do want to make an assessment of how accurate it is. Okay, how accurate your map, your classes are, how accurate they are. So it's important that you also have collected some information that's not used in the training. So ideally, it's either more ground truth or more observation of the initial data set here. Okay. And then what you could do is determine if the areas you said in your non-training data were accurate. So think about that. Like, let's say I have 100 more pixels, and in my 100 more pixels for forest, I go and check, and 90 out of 100 were actually classified as forest using the process that I did. Then I could say the accuracy is 90%. 90% of the time, it classified these blind samples that I didn't use in the training data correctly. And so I could say I did a pretty good job. Okay. Or I might say I did a bad job. So that's what the confusion matrix is, because I just did it for just forest. But if I had 7 or 8 classes, I would have 7 or 8 different values. And so we'll talk about that more when we get to there. But that's basically what the confusion matrix is the rows and columns of your different classes, and how many were accurate are the diagonals. In other words, how many did you say were forest, and how many were actually classified as forest? How many did you say were forest, but then were classified as water? That would be a problem, right? That's what we mean by the confusion matrix. So your overall accuracy is just the amount of pixels you got right in your withheld training and non-training data. Okay. All right. And then we've got commission errors and omission errors. These are the ones that you either incorrectly assigned to a class they weren't in, or if you look at that the other way, there are pixels in a class that were assigned to a different class. All right. There are several other algorithms. Some of these are implemented in ArcGIS, such as this one. The classification and regression tree analysis is another algorithm that's not maximum likelihood. It basically works by taking all of the bands and coming up with a regression. We didn't talk about regression in this course, right? It's coming up with a mathematical model to predict what a certain value would be based on all the other values, based on a linear combination of the other values. So that's implemented here, random trees classifier. The random trees classifier actually does that over and over, iteratively, a bunch of different times, does these regression trees over and over. Okay, neural networks and deep learning are also starting to be implemented more and more in in GIS software. Right now, it's kind of a decoupled solution where there are standard methods for how the data needs to be prepared for these deep learning neural network analysis packages. And so ArcGIS has, this is actually pretty new. I think it's in 2.2 or maybe even this version. It allows you to prepare your data for those processes, but they still require some programming knowledge to actually implement those. So I'd like to put some of that in the scripting class next semester, but we're not going to implement that for today. So right now, what you do is you prepare it, and it prepares the files, and then you have to actually implement those in a scripting environment, depending on which deep learning algorithm that you choose. There's a number of them. And then you run it outside and you import it back into ArcGIS once it's complete. Okay. All right. So it works. The way that those algorithms works is through this concept of a neural network, where there is the input layer, which is the training data that we talked about before. You really don't train it any different than you train maximum likelihood or the classification and regression tree algorithm. Okay, and then what it does is it goes through and it comes up with the simplest way to say this probably is that it comes up with a number of different cutoffs, and you can add additional layers to make it have more and more complexity. In other words, you're talking about more and more rules, more and more if-then statements, but it's coming up with these rules based on observing the data. So the more and more examples that you can give it, the better that it does. And so one reason why it's referred to as deep learning is that it has more and more of these hidden layers, which do cost more in computation, but even desktop machines are becoming capable of a significant number of layers inside of a neural network. Okay. All right. I'm gonna stop there. Let's see. So let's talk about what I want you to do for the lab. Okay. So if you go to the modules and you go to the image classification lab. So what you're going to do is ESRI has 3 different courses that talk about doing supervised pixel-based image classification that we did talk a lot about in today's lecture. So you're going to implement maximum likelihood there inside of this course. Okay. Each of these courses takes about an hour, probably a little less. Definitely a little less with this one and this one. I think they actually have, don't they have how long it takes estimated on there? Yeah. Yeah, I did this one right here, and it took me about 45 minutes. How long does that say? It says 1 hour. That took me about 45 minutes. And then I looked through these other 2. So the thing is that these do, as good a job as I could do at stepping you through some examples. You're going to download different data for these. You're not going to download this data yet, okay? But you're going to walk through the workflow. So you're going to press the right buttons. You're going to practice pressing the right buttons to get those processes completed. It's going to be fairly high resolution data. Make sure that when you do this, it's not going to, because I already did it. But when it first starts, make sure you select that you want to do it in ArcGIS Pro. Yeah, that was. So that's this high resolution data. And so it'll walk you through the process of actually defining these training data sets. Okay. And then implementing that. What I want you to do once you've completed that is to do it yourself, to actually implement it in using this data here. So we've got this this planet data, and what I want you to do is to use that data and then come up with 4 classes. Okay, you can subdivide them if you like, or if you think it works better. I think it should work pretty well. I actually haven't done it yet. To classify these data using just these classes, you might have to break up urban just a little bit and maybe forest just a little bit. But the rest of these, water looks pretty uniform in this imagery. And by open areas, I mean like fields. We don't really have, but you might have to break this up. Actually, now that I think about it, you might want to break that up into dirt, which is pretty rare where we are, unless there's a construction project going on, and like fields, open fields that are planted in grass or whatnot. Okay, and so you're going to produce a result here. Okay, and I should have put this, maybe I put this in the text. I'm not really concerned. We're not even going to evaluate the accuracy. Okay, I want you to try to make it look reasonable. But, you know, don't spend hours and hours trying to get a pixel to turn the right color by retraining your data over and over and over again, okay? Part of this is recognizing that classification is a bit of a challenge, okay? And so limit yourself to maybe 2 times through each, because you're going to use 2 different classification algorithms. Yeah, 2 of the techniques discussed. So you can implement 2 techniques, you choose them. But in other words, only run it 4 times at the most. So each one you could tweak it a little bit and rerun it just to see what the results look like, okay? But don't spend more than that amount of time, okay? Produce a result, that's the important part, okay? So you're gonna have to answer the following questions, which we've already answered the first one, but you can find that out. We answered who somebody was it Forrest that said, isn't that 3 meters? Oh, now I get the answer again. So you weren't, yeah, you weren't. Okay. So then, how many bands does this raster have? Which I already said. I already mentioned. So yeah, turn that in, and then this last one's kind of will require a little bit more text, maybe a paragraph or so. What challenges did you have at arriving at a classification? What might help us to arrive at a better classification? So that's why you might want to run it twice, just to see if it improved or didn't improve it, or your ideas there. Okay, so that's the process that you're going to go through. So you know, this lab might take you 4 or 5 hours or so altogether after you do these plus this. I believe you can do it pretty quick though, okay, depending on how quickly you can draw the training polygons. Okay, but remember, you want them spread out, and you want them to be good examples of that same of the same class. Okay. All right, does anybody have any questions about the expectation there? All right. Yeah, let's go ahead and take a break, and I'll see if I can log in and get that project that I created last week, and then we'll continue. So let's come back at 3 o'clock, because it might take me about 5 minutes to get that, and then we'll take a 10-minute break. All right. So let me experiment and.